Welcome everybody to the Johnson Matthey Platinum Group Metals Conference, Critical to the Future of Sustainable Technology. So what is the role of PGMs in the future technologies, or those technologies that are going to allow us to have a beautiful, sustainable and successful future as human beings on our wonderful planet? My name is Dr. Sarah Gordon. Now, before we get started, or basically the bit that you have all been waiting for, because of course this is a conference, and Emma, I'm going to invite you to maybe say some words against this particular slide, because of course this is a Johnson Matthey conference. There is a little bit of a legal disclaimer we need to flash up at the beginning in front of you. We will put this into chat as well if any of you want to read this in detail. This is the talk that certainly when we were putting together the agenda for the conference, I could work out some of the different areas. But what is this thing called spintronics, etc.? So Axel, if you want to start sharing your screen so we can make sure we can see your slides, and then I will invite you to introduce yourself and get going with your talk. So everybody, hands together for the fabulous Axel. Thank you very much.
Yes, hello. So I'm glad to be here. I'm from the University of Illinois at Urbana-Champaign. I'm in the materials research laboratory there, and I've been working for a long time on magnetic materials. And so what I will show you is how some of these platinum group materials are particularly of interest for something that's called spintronics. And so the first question obviously is, what the hell is spintronics, right? So let's get to that. So most of the electronic devices that you use are based on what's called semiconductors. And so in these semiconductors, over the last decades, we have use them for encoding information and manipulating information by moving electronic charges around. So essentially, we do a lot of charging and discharging capacitors. And it turns out the electrons that move around in these devices not only have an electronic charge, but they also have a magnetic degree of freedom, which is called spin. So each of these electrons has like a little magnet attached to it, essentially, when you move it around. And in all these semiconducting electronics, you completely ignore this fact that spin is also there in these devices. And over the last 4 decades or so, we started to appreciate that we can also use these magnetic moments for something useful. In fact, this was discovered in 1986 by these 2 fellows, Albert Fett and Peter Grünberg, who got 2 decades later the Nobel Prize because it really revolutionized how we did some of our information handling. So in particular, it allows us to put magnetic materials directly in solid state memory, for example, and this is a trend that's currently accelerating. But it also has a lot of new interesting physics, and I'll spare you some of those details, but I'll mention some of the physics that's important for developing these new devices. So before I get there, I want to point out that information technology is actually something that has a really high energy price associated with it. And many of us are not necessarily aware of this. I'm sure many of you use Google all the time for figuring out, what to use maybe platinum group metals for, I don't know. It turns out if you want to boil a cup of water, it takes about 80 Google searches to they use up the same energy that is required to make your cup of tea, so that's quite staggering, actually. It's because of all the information that you move back and forth in the process. And this really becomes a problem because if you look at the energy consumed for information technologies, it's kind of this orange line, and you compare it to the current energy world production. In about 10 years or so, you get to the point where all these information technologies are not sustainable anymore. And so we have to come up with technologies that really push the energy consumption down. And there's actually a physical limit, the minimum energy that you require. And you can see we're easily a couple of orders of magnitudes above this, the way how we do this right now. And just to illustrate that this is like a real issue, I want to compare the energy use of medium-sized city in the US, San Francisco, which uses about 6.6 terawatt hours per year in 2021, compared to Google, which uses about 2.5 as much. And more shockingly, the energy consumption of San Francisco increases by about 15% every 5 years. But the energy consumption of Google increases by 170% every 5 years. So these are numbers from 2021 and 2020, where Google used about 2.5 as much energy as San Francisco. By today, 2023, it's probably more like 4 times as much. So this is becoming a real issue, concern that we have to address in some ways. Okay, so let's take a little bit at what made information technology tick for the last decades along. You may have heard of a prediction by an engineer called Gordon Moore, who worked for Intel, who predicted early in the 70s that the number of transistors in the integrated circuits multiplies every couple of years in a specific way. And what is amazing is that this prediction that he did in the 1970s held pretty much up to today. So we have an incredible amount of transistors in our electronic devices. And we have now situations where we can have these rather complex computers in our hands that are much more powerful than some of those that we toyed around with when we were young students or something. And so the reason why this development is so energy intensive is all this digital computation relies on a very good separation of logical zeros and ones with a high energy barrier in between. And it costs a lot of energy to switch them back and forth and to move them around. And that's part of the reason why the traditional computation is very, very energy intensive. So a good part of how you do this computation is that you have memory where you store the information. And what you have is you have different systems that you use depending for what you want to do. If you want long-term storage, actually the best long-term storage, infinitely long, is using magnetic tapes. Then for some medium time, you use like magnetic hard drives. So this is what we are. And also, this is traditionally where magnetic materials play a role. But as you move the information closer to where the logic operation, you want to shuttle the information faster. And so this requires typically semiconducting devices, which are much more expensive, but also more energy hungry. Here, the memory is stored without the need of powering them all the time. Here, as you know, if you lose power to your computer, it also loses all the information that it has. So the trend now is to push these magnetism materials up on this pyramid to get them closer to where we do the processing of information. And there are some very active developments to get magnetic materials involved in the random access memory, but even in the cache, and thereby, by making these memories also non-volatile, meaning you don't need to power them, you actually reduce the power consumption of the whole system as a whole. And to just put this in perspective, the global semiconductor memory market, last year is of the order of $100 billion. It's expected to double around every 10 years, which is consistent with this prediction of Moore's law that we saw earlier. And currently, actually, so the semiconductor memory market is just the top of this pyramid. At the moment, magnetic memory is about 1% of this whole market. But over the next 10 years, it's expected to be more than 10% of the whole market. So now, what is the new physics that enables some of this work? It turns out that if you have certain materials, you can have electrons that have their magnetic moments aligned in opposite directions. If you pass a current through them, the scattering of these electrons can be different, such that electrons of one magnetic moment direction scatter upwards and the other one scatter downwards. And so you can inject then these electrons into a ferromagnetic layer where they can manipulate the magnetization, and then by comparing it to another ferromagnetic layer, you can use this as a magnetic memory element. And this kind of physics allows to do things at very high speed with very large endurance, and that makes it attractive for magnetic memory devices that are very close to how we operate things in logic. And it turns out there are a whole slew of new materials that allow for this effect of what's called spin-orbit coupling. And there's one measure called the spin-orbit torque efficiency that we want to increase in order to get the power consumption down. And so traditional heavy metal systems are around here, and some of these new systems really push us in this direction. And as it turns out, some of these platinum group metals play a real important role in this. Now, before I mention this in more detail, I want to say one more thing. Besides the classical computation issues where we value really high precision in numerical calculations, we also encounter a whole slew of different computational tasks now, where we have large amount of data because we have sensors everywhere, where we get lots of information about the world around us. And now, instead of calculating something precisely, we are more interested in classifying different pieces of information. Now, it turns out this kind of information processing doesn't require the very precise definition of 0 and 1. We may have a much more analog kind of concept of how we want to interpret our data. And so it turns out for doing this, nature is actually very efficient. If you look at a supercomputer that is built on this traditional paradigm where you have this very well-defined zeros and ones, like 2 hours north of me, just close by Chicago, there's a big computer called Aurora. These are some measurements of how you use the computational power, but it takes like 13 megawatts to operate this machine. If you compare this with the natural brain, like one of my colleagues here down the hallway, the computational power of the human brain is actually not that far from these supercomputers in some of the relevant metrics, but the power used is like 6 orders of magnitude less. So by getting inspiration of the way how nature does information processing, there's definitely a lot to be gained in terms of energy efficiency. And so one of the ways how this works is in the natural brain, you have neurons that oscillate in some statistical way, and the information is encoded in the frequency, how they oscillate. And it turns out the same physics that allows us to switch magnetic materials also allows us to make them oscillate. And we can make very small nanoscale oscillators that then can interact with each other, very similar to how the natural brain works. And so we can use the same paradigms of natural brains using delocalized information and massively parallel synchronous processing for gaining possibly a lot in energy efficiency. Okay, so now one of the main physics that drives this is what's called spin-orbit coupling. It's a relativistic effect. If you move electrons in an electric field, these electric fields look to the electrons like magnetic fields, which then interact with the magnetic moments that they have. And it turns out these electric fields are internal to the materials. They come from the nuclei of the elements that we're using in our materials. And therefore, these spin-orbit coupling effects become more and more pronounced the heavier the elements are. And so this ability to use electronic charge motion for manipulating magnetic states is much enhanced in heavier elements. And so if you now look at the periodic table, if you're interested in semiconductors, your playground is here up to the right. You have silicon, germanium, your combinations of this. If you're interested in magnetic properties, you want to play here in the middle. This is where the fun is. In order to have magnetic moments, you have to have unfilled, partially filled D states, or you can also use F states, but for the sake of spintronics, D states is where it's interesting. And so we like iron, cobalt, and nickel because these are true ferromagnetic materials that have magnetic order, macroscopic magnetic order. But then we like all the elements underneath it because being heavier, they provide this large spin orbit coupling, which allows us to manipulate then electrically magnetic moments. So to put this in perspective, for example, the spin-orbit coupling allows this electric manipulation, but it also gives stability to magnetic moments that you want for magnetic data storage. You want what's called a high anisotropy, which makes magnetic moments stable against thermal fluctuations. And so you see here's this anisotropy value, which is essentially a measure of how stable your material is. The larger it is, the smaller you can make the memory. And you see that things like cobalt platinum or iron platinum really stand out in having very high anisotropies. And so iron platinum is, for example, a material that's of real interest for magnetic memory. Now, we like iron platinum because naturally iron platinum forms an alloy that has individual layers. And so it has a well-defined direction for the magnetization perpendicular to these layers. But you can also just simply grow alternating layers of different materials, cobalt palladium, for example. And so if you make these layers very thin, you can get very high anisotropies and you like them to be perpendicular so that the magnetization has two stable states up and down, which then easily is encoded in zeros and ones. Now it turns out not that much is known about multi-layers with rhodium. The main reason is rhodium is really expensive. So if you want to do it in your physical deposition system, it's quite some high upfront cost to do so. But it turns out that there are materials involving rhodium that have some really intriguing magnetic properties. And one of them is iron rhodium. Iron rhodium is a very curious material because at low temperatures, it has a magnetic order which is called antiferromagnetic, where adjacent magnetic moments point in opposite directions, so they cancel each other out. So at low temperatures, it actually looks like it's not magnetic to the outside world. And then as you heat it up right around room temperature, suddenly you get a large magnetic moment and it becomes ferromagnet, kind of like iron on its own. And so you see a large increase in the magnetization and changes in the electrical resistance of the same material. And this becomes now interesting because you can combine iron rhodium with iron platinum. And so actually in this particular example, they use iron rhodium and a little bit of iridium in there. And now suddenly the field that you need for switching things becomes much, much smaller by just heating up the material because you give this additional magnetic moment, which makes magnetization switching much, much easier. And so the idea is to use this in magnetic memory devices so that at room temperature, it's very stable, it's very insensitive to external magnetic field, but by heating it up, suddenly you can switch it very easily. But aside from just this change of magnetic order and magnetic anisotropy, we can also use iron rhodium for these electric switching that I was talking about, where we flow a current through the iron rhodium and then switch the magnetization of an adjacent magnetic layer. And what's remarkable is when we do this, when iron rhodium is antiferromagnetic, the efficiency of this effect is very, very high. It's 300%, which is like a factor 4 or 5 higher of what you would normally see in commercial devices right now. So in terms of reducing energy requirements, it's very, very effective. To put this into perspective, so I said low temperatures, we have this high spin torque efficiency, and this is on this chart right here. So it's pretty much where we want to be in this scenario. Now, the problem is it decreases when for iron rhodium we go to this ferromagnetic regime. But not all is lost. By alloying a little bit iridium into the iron rhodium, we can actually push this transition to much higher temperatures. And so it's entirely possible that if we use this composition, some of this efficiency for switching magnetizations may become much, much higher. So we don't know yet. We haven't tried that out, but that's one of the perspectives. But besides just iron rhodium, there are a lot of other alloys that are of interest. I just mentioned here one which is called rhodium silicide. This one is interesting because it has a very simple crystal structure, which has no inversion symmetry, which is curious because now you can tell whether you pass a current one way or another, and that allows for this very efficient spin-orbit torque generation. Now, while this material looks promising, not much has been done yet, again, because the price typically scares many of the researchers away. But maybe that becomes easier pretty soon, so we'll see. I think my time is pretty much up at this point. So I want to just say, some of these rhodium-based alloys where they can really have impact is in this ability of switching magnetic states through electric means. So that can be either in traditional non-volatile memory, or even for new ideas where we use probabilistic computing to mimic more the way how the brain is working. So here's just a brief conclusion of the things that I wanted to convey to you, that magnetic materials are really key to today's data-intensive society. Pretty much all the long-term digital storage is already magnetic. The question is, can we push it also to the short-term where we actually manipulate information? And this may help then saving energy. And it turns out that these spin-orbit effects really are key to making this happen. And these platinum group elements are really particularly interesting for that. And for example, pretty much any spintronic device that you see nowadays already has a layer of ruthenium in there. And we'll see what we can do with all the other elements. Thank you very much for your attention.
Brilliant. Thank you so much for that, Axel. Everybody, round of applause for the phenomenal Axel Hoffman. Thank you very, very much.